Welcome to the electronicshobbyblog.com. I'm your host, Dominic Soldano, and today we're going to talk about MOSFETs. Metal oxide semiconductor field effect transistors, or MOSFETs, are amazing devices. They may look a lot like bipolar junction transistors, but they're quite different. They're capable of doing things that bipolar junction transistors just can't do. MOSFETs are designed to switch huge amounts of current. A MOSFET in a TO220 package could sink hundreds of amps and can handle hundreds of volts between the drain and source. MOSFETs also differ from BJTs in that they're voltage-controlled devices. In a transistor, a current flowing into the base causes a current to flow in the collector and emitter of the transistor. With a MOSFET, a voltage applied at the gate causes a current to flow from the drain to the source. In addition, the gate is isolated from the rest of the substrate by an oxide layer, which is a very effective insulator. So unlike BJTs, MOSFETs have very high input impedance. That means that a low voltage, low current device like a microcontroller using a MOSFET can switch huge amounts of voltage and current. In fact, MOSFETs are what allow microcontrollers like the Arduino to control powerful motors in robotics and other switching applications. Here's an excerpt from a data sheet from a typical power MOSFET. These are the MOSFETs I'm using in my LED photo light. You can see that this particular MOSFET can switch voltages up to 60 volts between the drain and source and can handle a drain current of 150 amps. With proper thermal management, i.e. heat sinks and fans, these can dissipate 349 watts. When used in switching applications at full on, these typically only have a 2 milliohm effective resistance between the drain and the source. Here's another excerpt from that same data sheet. These characteristic curves show how that MOSFET performs over a wide variety of gate voltages on the right, and specifically within the sub-threshold region on the left. The sub-threshold region is that region of operation where the MOSFET is not yet fully on. In the graph on the right, you can see just how quickly the resistance of the MOSFET drops as the gate voltage gets above 2.5 volts. And you can see how it increases dramatically when the gate voltage is below 2.5 volts. That's the threshold. Notice that the MOSFET is almost fully on at 5 volts. That's why these are normally referred to as logic level MOSFETs. They switch on and off using the same logic levels as digital devices. And on the left, we see how the MOSFET behaves in the sub-threshold region before the gate voltage gets high enough to turn it on completely. In this region, the MOSFET can be used like a potentiometer. MOSFETs come in two basic types, or modes: enhancement mode and depletion mode. Think of enhancement mode devices as a normally open switch, and depletion mode devices as a normally closed switch. Between those two modes, enhancement and depletion, there are also P-channel and N-channel devices. A P-channel device is controlled by a positive voltage at the gate, while an N-channel device is controlled by a negative voltage at the gate. Think of P as standing for positive and N as standing for negative. Some MOSFETs even have a built-in protection diode. Here's a table depicting how each of these devices behaves as a switch. For example, an enhancement mode P-channel device is off when the gate voltage is 0 and turns on when the gate voltage goes positive, while a depletion mode N-channel device is on when the gate voltage is 0 and turns off when the gate voltage goes negative. And here's a practical example of an enhancement mode P-channel MOSFET being used as a normally open switch, and an example of a depletion mode P-channel MOSFET being used as a normally closed switch. Let's take a look at the first example, the normally open switch, in the lab. I want you to pay particular attention to the 10K pull-down resistor. You'll see why that's important when you're using a MOSFET as a switch. I've got a power MOSFET set up as a switch on the breadboard, and I'm using an LED as the load because it's fairly convenient to see what's going on. Although these power MOSFETs are capable of drawing hundreds of amps. So let's see what happens when I apply a positive voltage at the gate of this MOSFET. This is an enhancement mode P-channel MOSFET. You can see when I apply a positive voltage at the gate, it turns the LED on, and when I remove the positive voltage at the gate, it turns the LED off. Notice also what happens to the voltage, the source to drain voltage. It goes way down because RDS, which is the on resistance for the MOSFET, goes way down to just a few milliohms. All right. Now I want to show you another interesting phenomenon that you need to pay attention to if you're using a MOSFET as a switch. You'll notice that I've got a pull-down resistor here. And if I remove that pull-down resistor, which I just did, and then switch the LED on, switch the MOSFET on, it'll stay on. It won't go off. It's kind of acting like an SCR. And so for a lot of these MOSFETs, you're going to want to use a pull-down resistor if you want it to turn off when the gate voltage is removed. And here's an example of a MOSFET being used to control current. In this example, I'm operating the MOSFET in the sub-threshold region. That allows me to control how much current is flowing from the drain to the source. And I can use it to control brightness, well, much like you would use a potentiometer. But in this case, a potentiometer that can control very large currents. I experimented with this particular MOSFET in the lab as part of my photolight project. And I found that when controlling the LED matrix, the LEDs began to come on when there was about 1.2 volts at the gate, and they were fully on at the point where there was 2.1 volts at the gate. The voltage divider you see at the left allows that potentiometer to go between 1.2 volts and 2.1 volts over its full range. This way I get full lighting control over the range of the 10K potentiometer. I didn't use that voltage divider in the lab example that I'm going to show you, and you'll see that I have a very hard time with precise current control. Without the voltage divider, only a very small portion of the 10K potentiometer's range is giving me the control. It doesn't take much of a turn to get past the threshold and put the MOSFET into full conduction. Here, let's take a look. You'll get the idea. And so this is the exact same circuit we had before, only now I've got a potentiometer controlling the gate. Let's see what happens to the current as I vary the voltage. So you can see that I can control it within that linear region and vary the current. And here's an example of 4 MOSFETs set up in what's called a bridge configuration to provide bidirectional control of a motor. When we apply voltage to the forward control pin, current will flow through the first MOSFET, through the motor to the right, and then down through that lower right corner MOSFET. So the motor will turn in one direction. If I apply a voltage to the reverse input, then current will flow through the MOSFET on the upper right, through the motor in the opposite direction, and then down through the MOSFET on the lower left. So the current is going through the motor in the opposite direction, and the motor will turn in the opposite direction. H-bridge configurations like this are very common in robotic and other motor control applications. We can also bias a MOSFET just like a BJT, and then use it as an amplifier. MOSFETs also excel as high impedance front-end inputs for instrumentation, like this example here. They're a great tool to keep in your arsenal of electronic components and design techniques. Well, I hope you enjoyed that, and that you'll be applying MOSFETs in your own applications. If you did, then how about a thumbs up and subscribe so you won't miss any new content. Until next time, Cheers!